All right. Hi, guys. Today I am going to be discussing with you the results of our pressure versus temperature lab. Now, to remind you, we gathered this data using the rigid flask that had the same number of particles, and we just changed the temperature. And this is temperature in degrees Celsius. So the first thing I'm going to do is make sure that you have your graph done correctly. It should look sort of like mine. If it doesn't, let's go through some possibilities of why it doesn't. So you can double click on this or click Edit Chart. And it should be a scatter chart, not a line graph. And it should have temperature on the x-axis. You can hear my cat in the background. She's saying hi to everybody. And then pressure on the y-axis. Double check, sometimes people have the label correct, but not the numbers. The temperature has lower numbers, the highest was 80. The pressure has higher numbers, the highest was in the hundreds. So if yours does not look like mine and it's labeled correctly, double check that it is in fact the correct data as well. So temperature on the x-axis because it was the independent variable, pressure on the y. Then under Customize and Series and scrolling down, this is where you add the trend line, and it is a linear trend line this time. And under Labels, say Use Equation, because this is where our equation is, and we do need to use the equation today. Now for the data, we're going to process the data in the same way we did for the previous labs. So for one column, I'm going to do pressure times temperature in degrees Celsius. I'm labeling that because later we're going to learn there's more than one way to measure temperature. And then pressure divided by temperature in degrees Celsius. And to remind you how to do this on the spreadsheet, first you type the equal sign because that lets the spreadsheet know you're going to do math. And then you single click on the pressure column and then star for the times and single click on the temperature column. Press enter and then click back and then click and hold on the little square and drag down, and that will do the same math for all of them. You can use these buttons up here to increase or decrease your decimal places. I have it set right now to the ones. Then for divided, same idea. Press the equal sign. Then you click on pressure. Then the / for divided. Then temperature. Press enter. Google will often anticipate that you wanted to do the whole thing, so I'm just going to say yes. If it doesn't, you would do the same thing where you click and drag on the little square. And I set this to the 10th place earlier, but you can set it to whatever place you want. So now that we have our data, we're going to think about it. And in our previous labs, in pressure versus volume, we saw that pressure times volume was a constant. And so we said since pressure times volume was a constant, the pressure times the volume at one point was equal to the pressure times the volume at a second point. Well, I think it's pretty clear here that this is not a constant because 57 and 9,000 are not the same number. Now, pressure divided by temperature. When we looked at the pressure in particles lab, we saw that pressure divided by number of particles was a constant. And so we concluded, since they were all equal to the same number, the pressure at one point divided by the particles at one point was equal to the pressures at a second point divided by the particles at a second point. Well, here, 157 and 1, not the same number, also not a constant. So unlike our previous labs, we don't seem to have a way to do math with this. It's not inversely proportional like pressure and volume, and it's not directly proportional like it was with pressure and number of particles. But let's look back at this graph and think about why that is. Remember, our pressure and particles graph went through the origin, because if there are 0 particles, there is 0 pressure. Well, this graph does not go through the origin, and that's because 0 Celsius is not the coldest temperature. 0 Celsius, if you'll recall from earlier, is the temperature that water freezes at. Well, that's not the coldest temperature. There's temperatures below freezing. I often say, remember Canada and Minnesota, even though it doesn't get below freezing often here, in a cold winter day it does. So the particles are still moving at 0 degrees Celsius and they still have pressure. Well, that kind of makes us think, if particles start moving slower and slower as we cool down the temperature, what is the lowest temperature we can get? Like, can we stop the particles? And if we did stop the particles, what would happen? Well, theoretically, if a particle stopped completely, then it would no longer have any pressure because it wouldn't be colliding anymore. So we can actually use our data here to figure out what is that temperature? What is that temperature where there is 0 pressure? And the way we can do that is we can edit our chart and go to Customize. We can make our x-axis extend until we can see where it crosses the x-axis. So if I extend the x-axis to -300, then now we can see that, in fact, at a little bit more than -300 degrees Celsius, we have this theoretical lowest temperature, the temperature at which all the particles stop moving and there is 0 pressure. Now, if you do the math with this, if you set the pressure to 0 and solve for that temperature, you'll get -291 degrees Celsius with our data. Now, in actuality, the real number is -273.15 degrees Celsius, because of course our data is not perfect data. However, it's pretty good considering. So I'm going to type it here. -273.15 Celsius is the lowest possible temperature. I can't type today. Lowest possible temperature. Now, there's a special name for this lowest possible temperature. It is called absolute zero. And this is all good, but remember, my problem was that this is not directly proportional. I do know that as I increase the temperature, I increase the pressure, but it's not proportional. When I double the temperature, when we go from 21 degrees to 41 degrees, which is approximately double, I don't come close to doubling the pressure. It only goes up like 6 kilopascals. So we can't do the math with it the way we did before. But there was a scientist named Lord Kelvin who realized something. He realized that if you invent a new temperature scale where 0 is in fact the lowest temperature, then that can solve the problems of being proportional. So what he said was, let's make -273.15 degrees Celsius. Let's turn that into a new scale, and we'll call that 0 Kelvin. Because of course it's named after himself, right? So 0 Kelvin is the other temperature for absolute 0. And this new temperature scale, if we want to convert Celsius to Kelvin, Kelvin is simply equal to the temperature in Celsius plus 273.15 degrees. So we can see that because if we had -273.15 and we add 273.15 to it, we get 0. So that is the lowest possible temperature. And now we can do a little bit of investigation here. I can make a new column, and I'm going to call it temperature in Kelvin. And to do my math here, I'm going to do equal sign to do math, and click on the temperature in Celsius. And I'm going to convert it to Kelvin, like I said below, by adding 273.15. And then I will click back and drag to convert all of my temperatures to Kelvin. And now let's see if we can do math with it. Now our graph, if we look here, is the most similar to the pressure and particles graph, because even if it's not directly proportional right now, when temperature is increased, the pressure is increased. And when we looked at pressure and particles, it was pressure divided by particles that was constant. So I'm not going to do the pressure times temperature right now because my instinct says it's pressure divided by temperature. That's the one I want. So pressure divided by temperature in Kelvin, I'm going to do equal sign, and pressure is over here in this column, column B, then divided by, and this time I will click on my temperature in Kelvin, not Celsius, and press enter. Wait a minute. Oh, I think I have it set to too few places. There you go. I was confused. All right, so make sure you're not like me and have it to too few places. And then I'm going to drag it to do it to all of the columns. Oops, I missed one. And if you look at this, although it's not perfect because our data is not perfect, it's pretty darn good. You can see that it's 0.34, 0.34, 0.34. The third digit changes slightly, but I would call that a constant, which means that in the end, our equation will look very similar to the pressure and particles equation. So that means the pressure at one point, P1, divided by the temperature at that point, T1, is equal to the pressure at a second point, P2, divided by the temperature at that point. And remember, the reason that is true that we discussed on our previous labs is that if the P1 divided by T1 at this point here, for example, is one constant, and P2 divided by T2, like at this point here, is the same constant, by the transitive property, we know that those two things are equal to each other. But there is a key important thing here, and that is only when we convert the temperature to, Kelvin. If we try to do this math with Celsius, it will not work because pressure divided by temperature in Celsius is not a constant. So a key thing to remember on all of our exams and doing all of your math is that you have to convert your temperature to Kelvin before you can do any math with it. And in case you're worried, I will always give you the equations on the test, so you do not need to memorize them. So now that you know how to process our data, oh, I almost forgot one last thing. I did make a graph with the pressure and temperature in Kelvin instead of Celsius. And although it's not perfect because our data is not perfect, you can see it does go very close to the origin. My actual y-intercept is 5, but that's just due to slight errors in the data. But it's very, very close to the origin, much like the pressure and particles graph. In fact, if the graph is unlabeled, the pressure versus particles and pressure versus temperature in Kelvin look identical. Unlike, remember, the pressure versus Celsius, where the y-intercept was in fact like 94 degrees, and it only had the x-intercept at negative 273. So what you're going to do now is you're going to finish worksheet number 3. That was the Pressure Lab summary worksheet, and finish writing up all about the pressure versus temperature lab. There's also a very short video about absolute zero, giving you some more information about what happens at absolute zero. A little side note about absolute zero is that for quantum mechanics reasons, it actually is impossible to fully get to absolute zero, but scientists have gotten very, very close, like 0.00001 degrees within absolute zero. So there's a little 2-minute video to watch about that. And then for those of you who are going for exceeds on the test, there is an optional reading about absolute zero that will give you more details that will be useful for the exceeds question on the test. All right, hope that was helpful, and I will see you all later.